take a look at the three pictures. Decide which one came first in time and which one came last in time. The picture on the right shows a balloon that's intact. It's filled with some kind of gas, presumably hydrogen. And it looks like there's a flame that is about to contact the surface of the balloon. Picture 2 shows an explosion, a chemical reaction between the hydrogen and oxygen, where heat is released and then disperses, we assume. And then picture 1 shows the remnants of the balloon on the floor. So we assume that picture 3 was actually taken first in time and picture 1 last. How do we know it wasn't the reverse? Well, first of all, which picture shows order and which picture shows disorder? That's a little tricky, but if you think back to the box of pennies example that I had talked about, and also the hot cup of coffee example, their energy had left the coffee and was dispersed to the surroundings. So if we use that same idea here, there's actually high order at the beginning. And disorder at the end. Which picture shows low entropy and which one shows high entropy? Well, the second law of thermodynamics implies that entropy increases as time goes on. So this one is actually low entropy. And this one would be higher entropy. The second law of thermodynamics says that systems will proceed from low entropy to high entropy if those systems are isolated. Do you think the process that we've shown here is a reversible process or irreversible? So, could it be that the balloon started off on the ground, actually, and that the balloon reformed into the picture we see on the right, the intact balloon? I think we can all agree that that is virtually impossible. But that's not really what it means to be reversible or irreversible. It doesn't mean that it's just unlikely. What it means is that the energy can't be gotten back. So it turns out that it is an irreversible process. And I don't mean that energy is destroyed. What I mean is that the useful energy has dispersed to the surroundings in such a way that it can't really be reclaimed. I'll try to explain what I mean. Assume the balloon started off full of hydrogen gas molecules, later ended up on the ground. It is extremely improbable, but perhaps not impossible for the reverse situation to happen. What would have to occur if the balloon were to reform on its own without help? So in other words, what would it take for picture 1 to actually be the first picture, and then number 2, and then number 3 came later? Well, the balloon parts would have to come back to the position that they were in originally, the reaction would need to be undone. So the hydrogen would have to be like unburned. Oops. Yeah. Okay. Particles would have to come back. Energy would have to come back. And then the balloon would have to melt into itself, creating the original shape that we had. It seems like a completely unrealistic, magical type of scenario. And it seems that way because of the second law of thermodynamics, which says that systems will proceed from order to disorder, not the reverse. So the second law is sometimes written as delta S over delta T is greater than or equal to 0. S stands for entropy, which says that the change in entropy with time will always be 0 or positive, never negative. And it implies that there's a direction that the universe tends to move toward. So it is not likely for a system to spontaneously proceed from disorder to order, and not likely for the balloon to spontaneously reform on its own. It's exceedingly more likely that the balloon's remnants would not find their way back. So imagine that you were to reform the balloon and you're going to help it out. And you want to take what is there in the environment now and put it back into order, basically. You want to impose order on the situation. What does it take? Well, you'd have to go around and collect the balloon parts. But would there be friction in doing so? Or would it be frictionless? Well, certainly there would be friction between your shoes and the ground as you walked around and physically picked up the balloon parts. Friction is a dissipative force, which means that energy is lost to the environment through heat flow, and that's energy that can never be gotten back, see? What else would we have to do? Well, we'd have to go melt them down. That would take energy. Into a new balloon. Would there be wasted energy in this process? Certainly. Not all the heat in that factory would be flowing to the right place. Some of it would be lost to the environment. You'd also have to collect hydrogen again. And that's no easy task. You would have to inflate the balloon. And you'd have to put it in place. All these processes require work. And whenever work is done in the real world, there's friction, there's air resistance, and there's heat flow. These are all dissipative ways that energy can be lost. So let's say that you do impose order on the situation. You reform it into what it once was. What would be the effects on the surroundings if you did carry it out? There would be heat flow, energy lost to friction. That's not destroyed, but it's transferred into the particles of an object. Like, you know how you rub something and it heats up, right? That's because the energy is being transferred into a heat form of heat flow, and that's how the energy is lost. Let's see, what else? Air resistance. Would reforming the balloon be an increase or a decrease in the entropy of the balloon? It would be a decrease. What this shows is that it's not impossible for systems to proceed from disorder to order. But this isn't an isolated system here. You're actually causing the decrease. But when you do that, you have to realize that what happens to the overall surroundings is that the surroundings entropy increases. The surroundings become more disordered.